Hello everyone, I'm Paul and today we're solving problem 2257, count unguarded cells in the grid. This is medium and it might seem tricky, so next I will show you what I think is an intuitive solution. We are given a grid with guards and walls. Now each guard can see in all four cardinal directions unless it's obstructed by a wall or another guard. So for example, if we take this guard, it can see up to this cell because here we have a wall. And our job is simple. We need to return the number of unoccupied cells that are not seen by any guard. In this case, we have unseen cells in green. So we have 1, 2, 3, 4, 5, 6, 7. So we return 7. Okay. Now let's see what's happening here. We have guards and they see in all four directions. So maybe we can check this cell, this cell, this cell, and this cell. And whenever we find a wall or a guard, for example, here we have a wall. In this case, we stop. And given that here we have empty cells, we can continue with these directions. So next we move to adjacent nodes again from these three, and now here we are out of bounds. From here we move to this cell, from here we move to this cell, and next we continue, and here we are out of bounds, out of bounds. And in case you didn't notice, this looks a lot like BFS. And in case you don't know what BFS is, we start from one node, and let's say here we have two adjacent nodes. Once we visit this node, we move to adjacent nodes. And let's say from here we have two more adjacent nodes, and from here we have two adjacent nodes. After we visit these two nodes, we can move to the next level and visit these four adjacent nodes. So as you can see, in BFS we are moving in circles, and it's exactly the same we are doing here. We start from this guard, then we visit adjacent nodes, then we visit adjacent nodes again, okay? Now the thing is that with traditional BFS, we would visit a node, let's say we start from this guard, and we go to all four directions. Next, we go to the next level, let's say we are standing at this node, and we repeat the same, we move in all four directions. But for this problem, we need to keep the same direction. We need to keep the initial direction. So if we decide to move up from this node, once we are here, we are moving up again. And once we are here, we move up again. And this means we need to keep track of the current direction somehow. So we can run a BFS from every guard and each time keep track of the current row, column, and direction. And this direction will never change. Let's say we're standing here. Once we decide to move up, for the next nodes, we keep moving up. If we decide to move right, for the next nodes, we move right, and so on. Now remember, as soon as we find some wall or guard, or we are out of bounds, we end with this direction. And we can store occupied or seen cells in a set. So when we end with this, we can just return the amount of rows, meaning 4, times the amount of columns, meaning 6. And this gives us the total amount of cells here. We have 4 times 6 cells, minus the amount of elements in the set. In this case, we have 17 cells in the set, so the result for this is 24 minus 17, 7. Overall time complexity for this is big O of nm, and space complexity is the same because we are keeping track of things with sets. We are using one set to keep track of every cell we see, and another set only for obstacles. So when we are at some obstacle, we know that we need to continue, okay? Now with this in mind, let's go with the code. we will have an array for directions. And here we are storing the numbers that we need to add to the current row and column if we are trying to move to any of the 4 directions. So for north, we add -1, 0. So let's say we are standing at some cell, we add this to the current row, and we add this to the current column, and we move north. For south, we have 1, 0. For east, we have 0, 1. And for west, we have 0, -1. And just to be clear, this is north, south, east, west. Now we will have a set for obstacles and another for the cells we see. Now we can see for every row and column in walls, we add to scene a tuple with the current row and column, and we add to obstacles the same, a tuple with row and column. And we are running a BFS here, so we are using a deck in Python because we want to pop elements from left. Now we can say for every row and column in cards, we add to scene the current row and column, and we add to obstacles the current row and column. And now we need to add to our queue the current guard, but we are moving in all 4 directions. So we can say for the in range 4 queue.append, and we are adding a tuple with the current row, column, and direction. This is very important. By doing this, we know where we are moving from every cell. Okay, so now we can say while we have something in the queue, row, column, and direction is queue.pop left, and direction row, direction column is directions at D. And the new row will be the current row plus direction row. New column is column plus direction column. And now we are checking if we are out of bounds, or meaning if this new row, new column corresponds to some cell that's out of bounds, or it corresponds to some obstacle, we need to continue. So we can say if new row is more than 0, or new row is greater or equal to m, or new column is smaller than 0, or new column is greater or equal to n, or we have a tuple with new row, new column in obstacles, we just continue. Else we add to the queue a tuple with new row, new column, and the current direction, and we add to scene a tuple with new row, new column. Finally, we can return the total amount of cells, meaning n times m, minus the length of scene. So this is the entire code. Now let's submit this and see if it works. As you can see, this works, and in terms of time and space complexity, it's efficient. Maybe you can make this more efficient with a different code, but overall time and space complexity here is big O of nm, which is efficient. So if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.